Good morning, good afternoon, good evening. I'm Martin Milton. I'm the director of the BIPM, and I'm delighted to welcome you today to this webinar, Developments Towards Interoperable Metrology. This webinar is being organized by us at BIPM together with CODATA as part of their global event, the CIDataCon 2022. So thank you for joining us. We have in our session today 6 speakers, all addressing topics relating to recent developments on setting in place new approaches and new services to provide interoperable metrology. I'm delighted today to welcome our chair, Dr. Alan Steele, a member of the CIPM. He's taken a great personal interest and a professional interest in his home institute at NRC in Canada in the topic of digital transformation. Alan's going to open the session for us with a short introduction to the work and perspectives of the CIPM on this topic, and then he's going to chair the session for the rest of the session today. We will end today with a Q&A session. Please put questions in the chat or save in your mind questions you may have, and we'd be delighted to have an open wrap-up discussion and chat session at the end. Can I hand over now to Alan Steele, please?
Well, thanks, Martin. It's great to be here and to participate in this this online seminar. Part of our outreach is to be inclusive and sharing what we know already about the SI. And I'm trying now, I'm sorry, I'm trying now to share my screen and to give you my slides. And I hope you can see my slides now. Martin, can you give me an indication that you can see them? Okay. You're on mute, but I saw the thumbs up, so unless I'm misinterpreting, I'll just keep going. So I want to talk about the CIPM and BIPM role in the digital framework. I'll be emphasizing the interoperability, which in our case right now also means great collaboration for metrology in the digital era. So just to give you a bit of background, you'll recall that the Meter Convention is a treaty that was signed as one of the very first scientific treaties in 1875. And of course, we're still going strong with over 100 member states and associates and implicating almost all of the world's GDP. Importantly for us today, the treaty itself creates the need to have and disseminate an international system of units. And those are foundational in metrology for precision measurement, for scientific research, and for industry and applications. Point that I was making about the importance of the international system of units is it's widely used in precision measurement and research and industry, but it also in the modern era over the last 20 years or so, it's formed the scientific basis for quality infrastructure. And that's the notion of standardization and metrology and accreditation. And of course, in our world, the most important standard for laboratory accreditation is ISO 17025. And now at this time, there are about 65,000 laboratories worldwide that are accredited to this, requesting traceability to the SI and using the SI for producing quality products and services around the world. This is a picture of the sort of the schematic of how those linked arms of accreditation, standards, and metrology work to promulgate down into the world of through the world of calibration certificates into the world of production, manufacturing, and so on. You might remember that our international system of units was updated, and I want to emphasize here the link with CODATA. When we switched over with the new definition and created a system of units that relies on defined values for some fundamental constants, it was the CODATA task group for fundamental constants that was tasked with taking all of the metrology data and optimizing it to give us the best values. So we have a long and fruitful collaboration from the BIPM all through all of the National Metrology Institutes and implicating CODATA. This system is extremely well established in what I'll call the physical or the concrete world. We have real artifacts or real things that we're measuring with real instruments and real calibration certificates. But as we move towards more and more digitalization and we move into a virtual or abstract world, we feel it's the right thing to do to make sure that the reliance that we have on quality infrastructure and the scientific basis of the international system of units carries over into that digital world. And to that end, the CIPM has a grand vision for its SI digital framework. There's a nice long document, but the part that matters for us today is that the long-term aim of our task group on digital SI is to establish a framework that meets FAIR principles. Those are the principles of findability, accessibility, interoperability, and reliability. Those are principles that are both in the data world of data and units and measurement and in the physical world of metrology. So meeting those FAIR principles and then allowing all aspects of the international measurement system, whether it's measurement results or the uncertainties, the traceability and the provenance of measurements, all of these things should be accessed and interpreted digitally, enabling machine-to-machine communication and analysis. So this goes far beyond just reading an electronic document in a PDF format. It means machines can take their calibration certificates, for example, and interpret them and perhaps even download the values into an instrument for making measurements. To this end, we have an expert group and a task group formed at the level of the CIPM. In the middle here, you see the name of our chair. He's the chair of the president of the CCU, and he's the member from Germany of the CIPM, and that's Joachim Ulrich. Also involved here at the BIPM headquarters is Director Martin Milton. And then in the light blue, you see the other CIPM members that are participating in the task group or providing support. And then the expert group, which is in darker blue, those are the real experts that are actually doing the work, creating the projects, and implementing the SI or evaluating ways to implement the SI in the digital world. Some of them you'll be hearing from today. But this is a very collaborative and broad-based activity. It's not for the CIPM and the BIPM alone to say, this is your digital system of units. We have to work together with others. We've already emphasized the importance of working with CODATA and working with standards bodies and accrediting bodies. And to that end, we've created a joint statement of intent, which has now been signed by these 8 lovely looking people who represent their respective organizations: ISO, CIPM, the International Scientific Council, CODATA, IEC, the International Electrotechnical Commission, ILAC, the Accreditation Cooperation, IMECO, an International Measurement Federation, and the OIML, which represents legal metrology in the world of regulation. And the bit that's important in this document is highlighted here, that we undertake to support in a way appropriate to each of our organizations the development, implementation, and promotion of the digital SI framework as part of a wider digital transformation of the international scientific and quality infrastructure. So it's a very, very large effort that we're going on right now. And we've already started working towards our long-term goal through the CIPM task group, our expert group, and our collaborations with other committees, such as the CODATA drum, which you saw earlier in the conference this week. The management and coordination efforts have culminated in some successes already with our first international workshop, which set the stage for deciding what do we mean for a digital framework, and that was at the end of last year. Our statement of collaboration is well underway, and we're already negotiating with other key stakeholders in the measurement and science community, and then we hope to bring them on board as signatories to the joint statement later on. And then, because the treaty is a formal construct, there's an international meeting of all the member states, which will take place in November of this year. And we have a draft resolution for that meter convention to support and endorse the work. And I'll talk about that at the end. On the technical development side, in addition to having our digital framework concept and the machine actionable and fair data services and tools, here at the BIPM, we'll be talking in this session about some of the work ongoing to evaluate existing ontologies and other programmable tools for bringing measurement units into your applications. We'll be speaking about the API for accessing the key comparison database where all of our high precision scientific results are collected online, and this will make it machine actionable instead of just human accessible. We're working on a machine readable SI brochure. The SI brochure is the document that contains the bones and structure of the International System of Units. But again, we don't want it just to be a PDF document. We want it to incorporate the framework for how you would use and manipulate and do dimensional analysis on the units. And then later on, you'll be hearing talks from two different consultative committees related to their thoughts on how we'll be moving towards digital dissemination of the units. The CCL is the consultative committee for length, and they'll be talking about realizing and disseminating the meter. And the CCTF, that's the consultative committee for time and frequency, and we'll talk about digital dissemination of timescales. Lately, we had a really nice high-profile success highlighting the collaboration, not only with the CODATA Drum, but other organizations in a Nature news bulletin that was in your news feeds on May 11th and made available as a comment in Nature Journal on May 10th. And you can see the title here, Stop Squandering Data, Make Units of Measurement Machine Readable. This is capturing the idea that we do well in the physical, the concrete world, but we have to do at least that well when we move to a fully digitalized framework for science and measurement. And to encourage the member states to participate and dedicate resources from their national metrology institutes, we've got a draft resolution which we'll be taking to the General Conference of Weights and Measures in November of this year when we all meet in Versailles. And among other things, explaining the context and the importance, this resolution invites national metrology institutes, the regional metrology organizations, and other stakeholders to maintain and, where possible, increase their existing level of commitment and collaboration with the CIPM to continue the development, promotion, and implementation of the SI digital framework. Once that mission is complete, we'll be just as well as we are now in the real world of quality infrastructure, and that's the future and vision that we see. And with that, I'll end my presentation. I hope to stop sharing my screen and hand things back over to Martin Milton to talk about his talk on giving an overview of the work here at the BIPM and taking over the next steps. Martin, can you hear me? Over to you.
Thanks, Alan. I think I'm all set there. Thank you, Alan, for the introduction. So yes, I'd like to talk and start to bring you an overview of the work we're doing at BIPM to develop new digital services. But I want to start by reminding us all, I hope we'd never forgotten, that metrology is a dynamic and a fast-moving area. It's a dynamic enterprise as we develop and advance what we do to serve our stakeholders better, and also to take advantage of new facilities and capabilities that have emerged from science and research. I hope we all are very familiar with what happened in 2018, the redefinition of the SI units. That was talked about as being the biggest single change in the SI. Well, I don't want to get involved in comparisons of superlatives, but let's recall that we've had many changes in the SI. We've had changes since the introduction of the brigading of the units under the title of the SI. We've changed things several times in response to new technologies and new abilities to serve stakeholders. We introduced the second based on an atomic definition. We introduced the meter based on the first definition of the fundamental constant. So we are working in a field, global measurement science, where things certainly change and where things are certainly responsive. We've done the same in our work program at the BIPM. In the 1960s, if we introduced ionizing radiation, it wasn't until the 1980s we became involved in time. Around 2000, we became involved in chemistry. And then I put at the end there, 2022 and beyond, question mark. This is the era where we are bringing a digital transformation into our services to best adapt them in the way Alan Steele said, so that what we did in a very solid way in the machine and in the, if you like, person readable world, we can do in a very solid way in the machine readable world. Alan's mentioned that there's a resolution will be discussed by our member states at the General Conference in November this year, and that will call the member states to commit to the work that the CIPM did to develop its so-called SI digital framework. I'll say a little bit more about this SI digital framework in my talk. But a central underpinning of that SI digital framework is it embodies the adoption of the FAIR principles, these principles that data should be findable and accessible and interoperable and reusable. So it's worth a short digression, I think, to recall where these FAIR principles came from. They are globally agreed. They were agreed initially as a part of the statement from the leaders of the G20 countries in 2016, who as part of their communique at the end of that conference committed to support appropriate efforts to promote open science and facilitate appropriate public funded research subject to the FAIR principles. So what do we mean by them? FAIR, of course, is findable, accessible, interoperable, reusable. To go a little bit into some detail about what these mean. When we say that data are findable, what we mean is that they're described by sufficiently detailed, rich metadata and registered in a searchable resource. They exist in a certain place in the web space, if you like. They exist at a certain point that can be referenced and reached. When we talk about data being accessible, we think about accessible data objects that can be obtained through well-defined and universally implemented protocols. So if we know where to find the data, we also know the protocol by which we access the data. It is always important as a note that accessible doesn't necessarily mean that data is open or free. There still may be, in some cases, a charge, or in some cases there may be an access requirement, a permission to access. But the principle that the data can be accessed through well-defined and universally implemented protocols is fundamental to FAIR. So that's the F and the A. And we always draw a breath then before we talk about the I and the R, because the I and the R bring with them a significantly greater level of complexity. So to think about interoperable data and metadata, these are those which use a formal, accessible, shared, and broadly applicable language. So information is available that provides users, provides readers with the data as to how to process and interpret this data. And then the fourth one, data is reusable when rich metadata and documentation meets relevant community standards. So this is the best case where the data can be found, we know how to access it, we know how to process it, and sufficient information about its content and properties that it can be used for a range of tasks. There's a great literature, of course, about FAIR. And if one has any questions, I strongly encourage you to look at some of that published literature explaining in many different ways what is FAIR and how to achieve it. My final point about FAIR is this small graphic on the right of the screen there, where I've illustrated by the size of the letters the relative complexity of the task of achieving those objectives. So whereas findable and accessible are tasks of similar difficulty, the task of becoming interoperable is quite significant, and the task of becoming reusable is quite significant also. So let me say a little about the SI digital framework. This is the proposed initiative from the CIPM, which will be brought forward and endorsed, we fully expect, by the member states in November at the General Conference. At the center of the SI digital framework, which has been developed by the CIPM, is a structure with 3 layers. At the bottom, if you like, in the center, is the SI core representation. This is the reference information agreed at the highest level that the SI depends on. The SI core underpins what we might call the service layer. These are services implemented by ourselves at BIPM, implemented by NMIs in open data formats that provide access, machine readable and machine implementable, of the SI core information. And then at the top level, we reach out to the user and the stakeholder communities with an applications layer, where new applications are facilitated by the services resting on the core. So how can the work in our BIPM laboratories and databases lead to findable and accessible data? Let's look at this application services core image again. I've expanded it there, and I'm going to introduce some graphics that are very much a work in progress as we work amongst the people you'll hear speaking this morning to develop a system and a presentation for how our work is knitted together. So that SI core is the BIPM core reference data that the SI depends upon. When we say, when we talk about the core reference, we're usually talking about the SI brochure. But of course, the SI brochure itself isn't only a PDF document, it's accompanied most importantly by the set of mise en pratique MEP, the detailed information about the practical realizations of all the units. These are absolutely essential part of our core reference information about the SI. Another important part of our core reference information is the information about the CODATA fundamental constants. They're absolutely part of our core. All of this information is currently widely and openly available. It's available in PDF formats, and it's available in HTML formats. So let's look at the service layer. Some of this service layer is in place and some of it's being developed. Let me explain. In the first level there, I've shown some databases, mise en pratique databases. So whereas our mise en pratique at the moment are currently PDF documents approved by consultative committees, they contain data, different types of data for the different CCs that are the essential information needed to realize the SI. Let me give just 2 examples. In the case of the CCL and the CCTF, the realization of the second depends upon the use of the agreed values for the reference frequencies, the corresponding wavelength values of atomic and ionic transitions that have been reviewed by the CCL, CCTF as being good to realize the second. So we have to have a way to move from the recording of those long numbers as agreed by the CCL, CCTF, to put them in some form of database that will enable them to be machine readable and fully used as part of this service layer. We're going to hear more about that in one of the talks later. That was one example, CCL, CCTF. Another example, which we've hardly started to explore yet, is the example of the information used to realize the ITS 90 temperature scale. That's a set of equations. They all exist in the PDF document. To make them machine readable, one would need a database structure whereby machines could visit that database to have information about the structure of the ITS 90. Those are 2 examples. I am sure that there are examples in all 7 of the base unit mise en pratique and the other mise en pratique we have associated with our other consultative committees. Above the mise en pratique layer, I refer here to the key comparison database, KCDB, with its 2 limbs, if you like, the CMC part and the key comparison, supplementary comparison part. We're going to hear a talk later from Suzanne Picard explaining the work that's going on to make the key comparison database, firstly in the CMC area, machine readable. She'll also make a reference to the work we're doing to extend the knowledge we've gained with the KCDB to make the JCTLM data similarly readable. Another one of our big data services is the provision of the data underpinning UTC, the Universal Timescale. That depends on the data from the CCTF, because it all is traceable back to the reference of the second. And we're starting a project to work with the CCTF to provide more information from our UTC database in a machine readable format. And we're going to hear more about that today. Finally, the applications layer, the most important layer. None of these new services achieve anything if they don't open up the possibility for new services, new digital services. The new digital service that's discussed most is probably digital calibration certificates, but I'm sure we know and believe that there'll be many others as well. So that is at what we call the data plane, the underpinning for findable and accessible data. But we want to go further than findable and accessible data. We want to produce data that's also interoperable and reusable. In order to do that, we need a set of additional references and information points. And we've, for the sake of presentation, we're starting to present these as being a parallel plane of facilities and services that we call the interoperability plane. So what's in our interoperability plane? Actually, it works just the same way as the SI digital framework with the applications services core principle. In the core are the definitions of functionality achievable through the VIM and the GUM. These underpin digital reference services. You'll hear in the next talk about the unique SI reference point, which is, if you like, if you want to call it, that is the digital SI brochure. But actually, it's a facility that provides the capability for interoperability. Then there's the extended VIM, which already exists on our website, which provides a very early implementation of how to provide interoperable access to the VIM. Then moving further into ideas that we won't have time to talk about in detail today, in order to have a fully functional interoperable system, we will need access to ontologies relevant to specific subject areas like length and temperature and all the other CCs, so that machines seeking to interpret that data from the mise en pratique are able to work out the relationship between the concepts they encounter. At a level above these services, there is already work underway on a unit mapping service. This is a service that provides, if you like, a translation between different metadata formats for the units. And associated with that are rules for using different digital services. So this is all a new and very exciting area, the interoperability plane. It exists to underpin and provide the new functionality, the I and the R functionality to complement the data plane. So in today's talks, as I've already mentioned, we're going to hear about the key comparison database and the follow-on to the JCTLM, the Joint Committee for Traceability in Laboratory Medicine database. We're going to hear about work with the CCL-CCTF data and how that feeds through into UTC data. And we're going to hear, I think, in the next talk about the unique SI reference point, which is a digital implementation of the SI brochure. So I just finished by saying, how can we at BIPM support digital NMIs? Well, I hope you're going to hear this morning, you've heard little from me, about how we're going to be supporting open data practices, how we're going to be implementing digital formats for metrology, and how we're going to be providing machine accessible data and reference information, all towards the objective to become the trusted hub for metrology data. So at that point, I'll say thank you very much and hand back to you, Alan.
Well, thanks, Martin. Sorry for the technical difficulties. People, the multiple screens is a complication in Zoom that's not finished yet, but nice job. Next, I'd like to introduce Janet Miles. She'll be talking about the unique SI reference point, a digital implementation of the SI brochure. So over to you, Janet.
Hi, well, I hope we've got this one right. So yes, indeed, unique SI reference point. And you'll see that I'm not going to be talking too much about a brochure as such. I gave you my first slide here, just showing you it is the implementation of the digital SI brochure. But we don't want in the machine world a brochure. We need something that the machines will be able to reference. I'm unable to move my slides up. Now, you all know the international system of units. It is really what allows the exchange of information, allows the comparability of measurements, is very much in interoperability. And the SI brochure itself is the reference where the community would go to get that ultimate reference, to get the definitions, to get the decisions, to get the historical information. And people know the SI brochure. It's getting increasingly long as the historical information grows. But it's very much where a person would go to understand what the definition is and perhaps why it's there. Now, in the machine world, the need is a bit different. We don't need, in the machine world, an introduction. We don't need rules about writing because the machines, they don't have the same understanding of capitals or bolds or italics even. What the machines need is very much the references. And so the heart of what I'll be talking about today is in chapter 2, chapter 3, and chapter 4 of the SI brochure. And of course, later in the day, you'll be later in the webinar, you'll be hearing about Appendix 2, so particularly from the CCL and CCTF. So we're used to, in our human readable world, being able to look up a document with PDF or web pages. We're also increasingly used to DOIs, which explain where to find that information. So what a machine reads is something similar, but instead of being HTML or PDF, it needs a structured data form, either structured files or a database. PIDs is just permanent identifiers, so it's something equivalent to DOIs, so permanent references for material that's available. And an API is the application programming interface. Is what allows the machine to go and read it. So it's like a subroutine in a computer program. So API is just an interface for the machine to use to go and get the data. So the key definitions in the SI brochure that we're trying to transform: the SI units, the SI prefixes, the defining constants, and in fact the non-SI units that are allowed with the system. But a machine readable version, I'll say it again, is not a book. Now, there's been a lot of talk about XML, and here I must say a special shout out to a colleague called Ron Say at Ribose, who's been extremely helpful in producing an XML version of the SI brochure, not just XML, but semantic XML. He's built understanding into it. Now, XML has been around for many, many years. It's a typical publication product. You would use it as a middleware, well, with middleware to lead to PDF, HTML, any other things. The problems are that it's quite heavy. It's only structured to the extent that the SI brochure itself would be structured. What's missing? Well, actually, you go back to what we said we needed. We need structured, fully structured. So you need to be able to identify what are the definitions. You need to identify the, well, create PIDs, and you need an API, of course. And definitely what you need is not a book. So the unique SI reference point is the name that we've given to the single point of truth that I see as the place people will be able to go to get the information, that the SI brochure itself will be able to go to get to the information, and machines will be able to go to get the information. So we're used to points of truth, such as the KCDB, which have a database and a person can look at it, and also an API, such as a machine can look at it. And in this talk, before going any further, I've got to say a few thank yous, particularly to Stuart Chalk, who has actually done the hard work of putting into place what I'm going to show you, the prototype. Martin and Milton and Michael Stock at the BIPM, with whom I've discussed various of the aspects. Ron Say, as I mentioned, at Ribose, has been an immense help, particularly with XML semantic understanding, but also machine interpreted, machine actionability overall. And there I mentioned some of the members of the expert group who have also commented. So with that said, and one further warning, this is just a prototype. The model can still be refined. And as Martin showed you, this is only one part in the wider digital landscape. It won't answer all questions on its own. With that all said and done, I would like to switch to showing you the SI reference point. So let's hope if this works. I should be able to, I'll say stop share, I think, and reshare my screen. My apologies. So this is actually an open address. I can put it in the chat and you can all have a look. It is a prototype. Oh, sorry, my microphone keeps moving. So the idea is to give information about the base units, information about the units with special names, information about the prefixes, and information about the defining constants and the allowed non-SI units. If I might start with a base unit, of course, here I'm showing you the human interface. For a machine, we would like the machines to be able to use our API interface, but it's just not so easy to show you that when you're a human. So these are HTML pages, of course. There will be a permanent identifier. This is the definition that comes directly from the SI brochure, give or take a few italics and things like that. Don't worry that they're not already. But one point we had to deal with was what information do we need to put in? So this, of course, it's not going to be understood by the machine. The idea is just that this is a reference that the machine can point to say when it's using a second or when something is described in seconds, this is what is meant. There are also, and in the brochure and just under the definition, a range of notes. So we've put these in, and it includes the relations with the fundamental constants. So there you might like to see that the equations have been coded typically in LaTeX and in MathJSON. The idea being that if a query comes in JSON, you can get the answer back out in JSON. If it comes in XML, you'd be able to get the answer in XML. And as humans, we're looking at HTML. We have our HTML. Now the SI prefixes, the orange ones are the ones that haven't actually been defined yet, but it's the same sort of thing. For a kilo, it gives the scaling factor and the, of course, the prefix. The derived units, well, here we have a derived unit for voltage with a symbol. You can express voltage in terms of the base units. You can express the volts in terms of other SI units. So if I click on this equation, again, you can receive it in terms of the defining constants as math.json, or we have it coded in LaTeX as well. LaTeX good if you want to make another PDF version of the SI brochure, you would want the LaTeX coding. So let me show you the defining constants as well. So again, each time we have a PID, a definition, any notes. So which notes are in here can be discussed. That's something for the relevant committees, particularly the CCU, to decide what exactly they need to put into here. But it's the structure that I'm interested in producing. Over here we have an API, which will just give you the get. We're not posting anything here. This is just for the information to for the computer to get to the definition, to retrieve the definition. I'm wondering if I should show you any others. I suppose in a second. Again, the API, it shows you the sort of code that you would get behind the scenes. Well, that in a nutshell is the SI reference point. So we're of course very interested in feedback. The point that it will be useful for humans, it will act as a reference for machines, and it will be fully fair, is really what we're trying to make. So on that, I think I shall stop and pass back to Alan or Martin.
Thanks so much, Janet. That was really interesting, and a lot of, as you say, a lot of work going on behind the scenes. So pulling back that curtain and showing us what it looks like was really interesting to see. Thank you. Our next speaker is Suzanne Picard. She'll be speaking about an API for calibration and measurement capabilities to underpin mutual recognition. Over to you, Suzanne.
Thank you, Alan. Now we will do like this. Okay, it's because, okay. I'm also into, so could you see the full screen? Can you see the full screen, Alan?
We see the thing that says you, oh, now we do. Yes, it just arrived.
Yes, you do. Okay,
Perfect.
It's very slow. Okay, thank you very much. Thank you, Alan. My name is Suzanne Picard. I'm speaking in my role as the KCDB coordinator, and I make a joint talk with Stephanie Maniguier, who's also my collaborator on the key comparison database, KCDB, but also in charge of the JCTLM database. So the KCDB contains approved, reviewed and approved data for CMCs and comparisons, and it's closely associated to the CIPM mutual recognition arrangement. We have made an application programming interface, which from now on we will call an API for published CMCs, and we will first speak about this. So if I recall the data plane with the application layer that Dr. Milton showed here earlier, we are speaking about this part, which is encircled in red. So if you go into the KCDB web, you can search on CMCs by clicking on the web page. And what happens is that there is being sent to a server, to the server that contains the data. And that server, via software and protocols, will give back the result, the targeted results, and you will see that on the screen. With an API, you will have an interface allowing you to program a query that you will send to the server, that will be sent to the server, and back through software and protocol will be delivered machine readable data that you required. So the idea is that no matter if you click or you program a query, you can almost in the same time query the same database. So that's the API functioning that we'll speak a lot about today. The advantages for an API for the KCDB, it's that first, I shouldn't say first of all, but it's the closest target is to provide machine readable data that can be included into digital calibration certificates of metrology institutes. It will be possible to follow the life cycle of a CMC by being the possibility to access obsolete data, which is not possible through the direct screen today due to the definition of the CMCs and their display. It is possible to enlarge statistical data treatments, and it's also possible to combine CMC data with other types of information, such as big data. And also a part is that it's possible also to adapt the contents to other languages than English. To get access on information on the API KCDB, you can go into the KCDB homepage. In the very bottom, you will get access where you will find a header called API KCDB. And if you click on that, you will find a few information on the terms of use and license. And then further, you will have a blue spot here. And if you click on that, you will find something that recalls also actually what Janet showed here previously. This is the a software giving you examples on how to use the API, giving you the possibility to query and get the results directly on the web. So you have a CMC search data controller, a reference data controller, or also schemas in XS for XML in XSD. And you have two possibilities to make search. Just as on the web, you have a possibility to do advanced search using a menu-based search facility, or quick search, where we mean that you can add search words. So these are the four possibilities. The queries and results can be combined or used, can be combined or simply used in XML or JSON. And we also have made an extensive user guide for users that are not acquainted with the contents of the KCDB. So this is a little bit to fulfill the R in FAIR, and that is also accessible here in the. So I will not make a live demonstration, but here's an example of a query on advanced search. And to the left-hand side here, you can see in yellow, this is the expression of a query where we have requested in electricity and magnetism, DC information on CMCs in DC. And we have also added a keyword voltage. These can be several. So this is an example. The country that has been selected is Japan, but you don't need to include some of these queries. You could query, for example, all countries. So this is an example just to reduce the number of outputs of this request. To the right here, we see an example of the results. The left is in XML, the right is here in XML, but as I said, you can get this in JSON. And the result here is cut off. It's just a part of the results, but where you get information, the information on, for example, the KCDB unique code. Each CMC has a unique code, no matter if it's obsolete or not. Each item in the KCDB is individually recognized. You will find which is the area you were searching for. It was Japan, the institute, and so on. And then you will also get coding on the CMC values for the measurand itself, and also its uncertainty, and of course the units. Dr. Milton introduced the concept of fair, findable, accessible, interoperable, and reusable to permit a universal exchange of data. That's the target of this. And we believe that the KCDB API, as it presently is being presented, it fulfills that it's FAR. It's findable, it's accessible, and it's reusable to the extent that we have in detail explained and described the contents and how to use it. On the contrary, to obtain the interoperable part, we cannot do that on ourselves. We need to have a consensus between more than the KCDB office. So here is an example within the expert group that we have talked about earlier. The expert group has developed a preliminary data model. It's a robust model, and where each data set or quantity actually contains 4 items. It will contain a number and a unit, of course, but will also be supported by a quantity kind and the scale of the quantity. So here, for example, we have an example of 3 microvolt. It's represent voltage, and it's a rational scale. And to this is being developed a so-called M layer, where M could stand for metrology, but also metadata, and it's a layer that will contain more information about this kind. For example, if it was voltage, voltage is enough to know how we will convert, for example, microvolt to volt, or to other units if this was the case. But it doesn't tell, for example, if it's AC voltage and DC voltage. On the first point, this is not important, but to be able to, for example, calculate with this, you would need to know if it's DC voltage and AC voltage in certain cases. So that are parts that would be going into the M layer, and this is being developed, so I will not go into those details. The quantity kind has also another function. If we take the example, for example, what you can find presently in the database is, for example, you can find information on mole fraction and mass fraction. And both of these could be indicated as dimensionless, although mole is mole per mole and mass would be, for example, kilogram per kilogram. But if both are dimensionless, you would have a tendency to add 2-dimensionless entities. And of course, you can't do that. You can't add mole fractions with mass fractions. So this is another example where the quantity kind is important to include into that data model. I'm sorry, I jumped here. So if we go back to the slide where I showed you the example of the results, I've just picked out here a little bit bigger so we can see it easier. You will have the unit, which is explained in volt, represented by the V, because that's how we read it. And the unit of the uncertainty, which is expressed as microvolt with this sign as we read it. And the quantity value is directly linked to the services that have been defined by the Consultative Committee of Electricity and Magnetics. Or here we have DC voltage sources, double dot, single values. But a machine would not understand this. So that is why we need to make this interoperable. We need to speak a common language, and that's where will play a very important role. So the V in volt would be replaced well, the V in volt will of course be displayed so people can read this, the humans can read it. But for the data that will be exported by the API, we need to apply a web ontology for the units and also for the quantities. So all data, including metadata, it needs to become interoperable. And to do that, we use a recognized system, which in our case is the SI system. So that's the very basis. We apply standards, and there's a variety of standards which have been mutually recognized. I have only made a few examples here. In each example, there are only a few examples. And as I said, we need to apply web ontologies. I have given 2 examples which are particularly applied, that could particularly be applied to metrology, but there is a wide range of other ontologies existing also for this. So this is the basis to make the KCDB CMC data fair with the I, with the dot on the I, if I can say. I will also take the occasion to present just 2 slides on the work on the JCTLM. JCTLM stands for Joint Committee for Traceability in Laboratory Medicine. And the contents is closely linked to the KCDB, who also contains information on reference material. So the JCTLM contains reference materials and analytic methods that is consultable via the web. And the data is also reviewed and approved by a committee, so it's controlled data. Presently, Stefan is in charge of refurbishing the web, so to make it a more up-to-date web, but included in this is also a complete refont of the database. And associated with this, there will also be an API JCTLM realized, and that will of course provide machine readable data, but it will also become interoperable using and applying a web ontology a little bit in parallel what I have already shown for the KCDB. So that work is well in progress. And with that, I say thank you for your attention. I will give back the word to Alan Steele. Thank you.
Thank you, Suzanne. Again, an excellent glimpse behind the cover, and seeing all of the work and progress that's going on is very encouraging to me. Next, we have Frédéric Mainadier, and he'll be speaking about machine-readable data within the context of disseminating the Coordinated Universal Time, UTC. Frédéric, over to you.
Thank you very much. Hello, I will present you the status of our work on making UTC data machine readable. And this is a teamwork, and I will speak as a member of the BIPM type department, but I want to acknowledge the work of Aurélie Arménie, who did most of the design and implementation of the API I am about to show you. So first, to give you the context, I would like to explain you what is the process of UTC calculation. Our task at the BIPM is to gather the data coming from atomic clocks all over the world. So roughly 450 atomic clocks coming from 80 laboratories, roughly. And thanks to time comparison by satellite, be it GNSS or telecom satellites, we're able to make a weighted average of all those clocks. And this gives us something that is called the échelle atomique libre, EAL, which is stable but not accurate. The second step is to bring in frequency steering by a handful of devices, about 10 devices around the world, which are atomic fountains or so primary or secondary realizations of the second, that allow us to get the accuracy and bring the accuracy to the échelle atomique libre, and the mix of the two gives us the temps atomique international, TAI. But that's not the end of the story. There's a first a third and last step, which is linked to the origin of our timescale, which is the rotation of the Earth, the motion, apparent motion of the sun in our sky. And to keep in sync with the rotation of the Earth, we need to monitor the position of the Earth with respect to the distant quasars. That's done by an institute called the International Earth Rotation Service that monitors the position of the crust with respect to quasars and tells us when we need to introduce leap seconds, that is additional second that we insert into TAI, and the TAI plus the leap seconds equals to UTC, Coordinated Universal Time, the worldwide time reference. Just note that this leap second issue is now very troublesome in our highly connected world. A solution would be to loosen a bit the tie between UTC and the position of Earth, but allow more than 1 second slack between the two. These discussions are ongoing. End of the parenthesis. Anyway, UTC is recognized as the only recommended timescale for the international reference, and it is materialized in our monthly publication, the Circular T. So here is an example of such a circular. As you can see, it's mainly a table with each row devoted to one local realization of UTC. That is the best prediction that laboratories are able to do of UTC. And the columns, each column is one date. So every 5 days, we tell what is the difference between the best guess the laboratories have, the UTC-K, and our final calculation of UTC. And you should realize that UTC is a posteriori calculation. There's no physical signal. We need to gather the whole month of data, then wait for additional data, for example, orbit of the satellites, then perform the calculation, carefully validate it by hand sometimes, and it takes a few days. So in a way, our job is to tell you what time it was 4 weeks ago, but we tell that at the nanosecond level. Of course, this means that you have a continuous flow of data and that we also need a way to disseminate the results. Circular T is published by the BIPM since 1988. That is the era of telex. And at that time, a lot of data was hand-typed on this kind of machine or issued on paper. So historically, the earliest issues of the Circular T were printed on paper and then sent by regular mail. But soon the computer data transfer emerged, especially among universities and academic institutions that generally host national time references. So TimeLab department was thus an early adopter of all the communication means offered by digital transformation. Automated data transfer on FTP, for example, either for the data collection from the clocks or for the Circular T dissemination. They exist since the 90s, and the data is already largely available through our website, enriched by plots now, HTML version. It's the latest version of the Circular T. You can click and have plots and have links to various references. Sorry. But it is still meant for humans. Someone comes to the website, reads it, and then takes the data. We do our best to keep this format machine readable in a way. You can parse the ASCII file that still exists, but it's not a guarantee of stability and so on. So there's a next step to be done, and that is machine readability through an API. This is the basic scheme of the API. You send a request to our website called webtai.bipm.org. Itself speaks to the database, sends a SQL request, gets back a list of data, and sends it back in a standard format, which is in our case JSON, but we could imagine other ways. Sending the request parameters to the URL is a very simple and very interoperable way to do it. The scheme is currently developed in-house completely, and it's still in a beta stage. This means that the interface is not yet fixed, and it may be subject to changes. And also, we have not yet included all what we think would be useful. So apart from the timescales, UTC, UTCR, GNSS timescales, for which we already provide the service, we plan to include other data, for example, calibration, following requests from our partners, our laboratories contributing to UTC. And we welcomed a few days ago our colleague from CENAM in Mexico, who will spend a few months with us and help implement that together with Aurélie, who did most of the work on this so far. So one notable feature is that we currently send only raw numbers because we are waiting for a decision about the representation of units as they should be within BIPM. In fact, the ideal state would be to link to the future single reference point of the SI that you have been shown before. Just to illustrate how easy it is to use the web server, here are some examples of scripts that may retrieve the data. If you are used to the programs like wget or curl, which are command line programs on Linux but also on Windows, you just type in the URL with the correct parameters, and then you get the data back. If you embed it in Perl or in Python or in whatever language you like to use, there are some libraries to discuss with a web server and to read JSON. So it's a very concise piece of code that already enables you to get it. Here I can show you a more elaborate example. This plots the data for a given laboratory and a given year, and it fetches all the data for 1 year. Here it's for the PTB laboratory and for year 2020, and then it prints some statistics, the maximum difference between the two in absolute, and then it plots the data. And as you can see, it's a very concise piece of code that already enables you to generate a kind of certificate. Of course, you have to put all the necessary text around that, but the basic data is there, and it's really easy to get. So I would like to conclude. This work is still in progress. So if you are interested, please visit our webpage and try the interface. Tell us what you would like to have. We have limited powers, but we can implement things. Feedback are welcome. And with that, I hand over the floor back to Anand. Thank you.
Really excellent. And again, I'm very much enjoying the amount of progress and the behind the scenes. I was a little bit reassured, Frédéric. Thank you for showing that some of it's actually quite simple. So that's nice to see. Next, we have Andrew Lewis from NPL speaking with Gianna Panfilo, also from the BIPM. And our talk will be entitled Realizing the Meter with a Digital Traceability Chain for the Recommended Optical Frequency Values. So over to Andrew and Gianna. I'll leave it to you.
Okay, hopefully I'm in full screen mode now. And you've got the presentation.
I can see it, yes. You look
Super.
good.
Good. As Alan said, this is a joint presentation, but I'm actually going to be the only speaker, but the presentation has been put together by myself, Andrew Lewis at NPL, and Gianna Panfilo at the BIPM. And we're talking about realizing the meter with a digital traceability chain for the recommended optical frequency values. And we'll talk a little bit more about what these specific items are later in the presentation. In a quick outline of the presentation, I'll talk a little bit about the work of the CCL, the Consultative Committee for Length, where this work has been initiated. A quick recap of the SI unit of length, the meter, and in particular its realization, because not everybody here might be a length metrologist. I'll then talk about how we can digitalize the SI meter at the highest level, and there are 3 approaches needed here, and you've seen one of them already in Janet's talk. And I'll then talk in more detail about this third part of digitalization of the meter, which is the digital aspect of the mise en pratique data. I'll show an example of how this might work in practice and give some ideas about how this might be a benefit to various users. So the CIPM Consultative Committee for Length has been around for quite some time, and its critical activity is really around the definition and realization of the meter, the unit of length. And it shares a responsibility with another CC, the Time and Frequency Consultative Committee, for something which is called the list of recommended values of standard frequencies for the realization of the meter and the secondary representations of the second. And my talk will focus on the digitalization of this aspect of the work. The CCL also has a task group on digitalization, and this work has been started under the auspices of this task group. So what is the meter? The SI brochure and soon the unique SI reference point will define the meter. The definition is on screen. It relates to the speed of light and also to the unit of time, second. But when you come to make practical use of the meter, you need to refer to the document, the mise en pratique, the putting into practice document. And that tells you how you should go about realizing the meter as a physical standard related back to the definition. If you look into the mise en pratique document, you'll see that, especially for macro scale metrology, so things which are not too large, then the preferred method of making measurements tends to be using optical interferometry, and you get the traceability through the interferometer. But to do that, you need to have the optical frequency of your light wave known. And there are essentially two ways of doing this. You either measure the frequency, for example, you use a frequency comb and link it back to the second, or you can use one of the standard frequencies, which is in this list, which is jointly maintained by the CCL and CCTF. If you go to the BIPM website and look for this list of frequencies, you'll see a screen somewhat similar to this. And you'll see that it lays out what are effectively buttons which you can press. On each button, it labels the particular frequency or the corresponding vacuum wavelength. It tells you a little bit about the atomic species which is being used, and it gives you the last time this information was updated. And that's a critical part about quality systems, which is making sure that the information which you're using is up to date. And I'm sure we all check back to this web page very frequently to make sure we're using the latest values. The frequencies cover quite a wide range and quite a good range of wavelengths, and they also include a few special items such as the rubidium frequency and some spectral lamps. But if you click on one of these buttons on the web interface at the moment, what do you see? Essentially, you get presented with a PDF document, and the PDF document is data rich. So it tells us things like the atomic transition of the particular frequency which we're interested in. This is the well-known 633 nanometer red laser wavelength. It tells us what the recommended values are that the CIPM has approved for the frequency and the wavelength, and what uncertainty you might get when you stabilize your laser. It tells you about the way you should be stabilizing the laser. But it then tells you what I'm calling critical metadata, which is if you want to achieve all of the things above, then you have to take care about certain operational aspects of your laser, such as the cell wall temperature, the cold finger temperature. And these are really quite critical. If you don't achieve these specifications, then your laser won't be achieving the uncertainty given above, and it won't be the frequency value which the CIPM has recommended. So these are really critical items needed by the person that's doing the experiment, that's doing the calibration of a customer laser using a laser. If you scroll down the document, you see lots of interesting source data. And if you continue down the document, you'll get to a very data-rich environment where you see other components of the same transition are listed with their frequency differences from the main transition. You might then find a second transition, which is nearby, which you can use, and in this case, even a third transition. So this is really a highly data-rich environment with lots of digits quite frequently. And if you're going to use the data, you have to make sure that you transcribe it very accurately into your own calibration system. So the situation at the moment, if you're a length metrologist and you want to calibrate a customer's laser and give traceability to the meter, first of all, you will have read the SI brochure to work out what the definition of the meter is. You will have picked a transition from the list of frequencies. You will have built a laser that follows the guidance in this text-based document. You'll then be operating the laser to do the beat frequency measurements. You'll be using data from the frequencies list as a critical input parameter. Of course, you'll be checking to make sure that your laser is operating within specifications all the time. And in between doing calibrations for customers, you will also be checking to make sure that the values you've read from this PDF document haven't been changed. Now, the CIPM does occasionally change the values in the document when more data is made available. Sometimes they relax the parameters, sometimes they tighten them up and make small adjustments to the frequencies. And you really ought to be checking to make sure that you're using the most up-to-date data all of the time. Martin spoke early on about the reliance and the quality aspects of the SI, and this is a critical aspect of this. If we think about what's going on here, these are really analog processes. They're based upon, at the moment, documents that a human has to go and find, read, and then understand, and also be aware that documents can be updated at any time. Now, to me, this sounds like a really good part of the traceability chain, which could be digitalized. And if we sit down and think about what's needed here, there are actually 3 tasks which need to be performed. First of these is at the very top of the traceability chain, and Janet has given us a really good overview of the work that's going on there at the moment regarding the unique SI reference point, which is the, if you like, the digital implementation of the SI brochure. So that's already underway at the top level. Some work which is going on behind the scenes, and here I thank Jana, my co-author, for providing some early view of this. This is the digitalization of this database of recommended frequencies. At the moment, this set of frequencies exists as a series of text documents, and CCL and CCTF want to be able to get access to the data. They want to be able to update the data. They want to be able to query it and do things with the data. And doing that with text documents is not ideal. And so this list of recommended frequencies is being transformed into a database, and this is an early site of that part of the database. Third aspect for giving this fully digitalized traceability chain for these reference frequencies concerns really the frequencies, but also this metadata, the cell wall temperature, the implementation specifics. These are understood by the scientists that are operating the lasers and are probably encoded into their measurement procedures, which are subject to their quality system. But what if something changes? So what happens if the CIPM revises one of the values in the list? Do the scientists automatically know about this? Maybe you've been on holiday when the change happened and you come back and you don't know that you're now using out of date values. Are local conditions assumed valid? So maybe the cell wall temperature was allowed to be 20 degrees Celsius and your laboratory is at 20 degrees Celsius, so you haven't really taken care of this. But what if the specifications now say 19.8 is an upper limit? Is your room still valid for performing these calibrations? Have you got any typos when you transfer this long digits into your software? And are you using the version which has the latest updates from the CIPM? If we can make all of this critical data digitally accessible, for example, as XML encoded data, then we can automate a lot of these behind the scenes issues which are there for fulfilling the quality requirements for giving access to the SI through these lasers. If we think about the traceability chain in terms of where it sits in the SI, we have at the very top the meter definitions, which then go through to the SI brochure or the unique reference point. We have the mise en pratique documents, which are the expert's summary of how you should go about this with input from the CCL and CCTF. And then below that, we have the various NMIs realizing the meter according to the mise en pratique, maybe with different lasers at different frequencies. They use those to calibrate customers' lasers. The customers put them into interferometers, which go into measuring machines and so on down the digital traceability chain. So this third aspect that I've been talking about for digitalization of the meter through these frequencies sits at this critical interface here, highlighted in yellow. It's the interface between the BIPM and the NMIs. Now, at the moment, this is a kind of a split interface because the BIPM publishes the documents and assumes that the NMIs read them and take the data down into their calibration systems. If we transform this into a digital aspect to make this data available from the BIPM, then this yellow area can be part of the role of the machines. They can operate in this regime here, interfacing with the BIPM. So what might this look like? So here is a customer calibration of a laser. So we have a customer laser getting its frequency from a reference laser to an NMI. And when that calibration starts, the NMI makes an API request to the BIPM and says, please give me the MEP data for meter realization of a standard frequency at 474 terahertz stabilized to iodine. The BIPM server responds with all of the data which is required, and it does this in a highly interoperable and reusable way. It uses a very strict coding of the data. So rather than coming back as a PDF document, it comes back, for example, in the form of XML. And the XML we'll look at in a moment is very structured. The meter realization system at the NMI receives the data from the BIPM, looks into the file, pulls out all of the critical numbers that it needs. Maybe it's this very long SI frequency value here, uses that as part of the calibration of the laser, and then the laser calibration is complete. The XML schema, there's a link given here, which is a draft schema, which myself and a colleague, Dr. Lancaster from MPL, have been proposing. And it's an XML schema based upon the digital SI data model, which is a model which has come out of an international project called SmartCom for representation of the SI in digital format. And our schema complies with this format. It has 5 elements, and they're listed here: the standard frequencies, the uncertainty components, rules about the implementation. So this is like the cell wall temperatures, the actual optical transitions themselves, and then all of the extra data, which gives you the offsets. Essentially, it's that big long list of the table that was in the PDF document, but in a digital, machine readable and parsable format. So here's an example of using this prototype schema for bringing data back. And again, we're looking at the 633 nanometer, the classic red helium neon laser. On the right, you can see the PDF document, and on the left, you can see the XML format of the same data coming back. And you can see this nice one-to-one correspondence. But if we zoom in a little bit to one of the values, which is this SI value of the frequency, and it's reproduced in the bottom right of the slide, you can see that all of the critical values are inserted between these tags, which means that the software at the NMI, which is controlling the laser, can ask through structured queries into the XML file to get this data back, and it gets it in a very rich format. It gets a value, a unit, an uncertainty, including the coverage interval and distribution. So it doesn't just get the frequency value, it gets a lot more data coming back at the same time. So this is an example of what one of these XML files would look like coming back from the BIPM. So the laser calibration system at the NMI takes in the BIPM metadata, which it's just downloaded, but it can also add additional metadata from itself. For example, it might be able to read the laboratory temperature. The operator might have entered in the serial numbers of the lasers that are in use. It might be able to read the current operational status of the laser, for example, which transition it's locked to. And so that is all part of this calibration of the customer laser. And when the laser is returned to the customer, the NMI makes the calibration data available either as a digital calibration certificate or as downloadable data from the NMI server. And it doesn't just make available the frequency value plus the uncertainty, but it also offers this rich metadata format. That has several advantages. So first of all, you have both parts of the traceability of the calibration. It has the physical data, the physical frequency of the laser, but it also has this authority and validity metadata, which is also important for quality aspects. It should get rid of transcription errors because the data is all encoded in machine readable format from end to end. And the software at the NMI can be checking to ensure that it's using the latest value by downloading it from the BIPM. It should be fully transparent. It should be traceable in terms of both the data and the authorization of the data to the SI and the CIPM. So that gives an added sort of bonus, because now the customer who receives the calibration data suddenly spots, if they look into the details, the fact that we're citing the BIPM and the SI at the top level of the chain. And that can sometimes be forgotten, that there is this link between the data you receive as a customer all the way back to the SI. The NMI can be adding its own metadata, so it can add value as part of its service for the customer. And of course, the customer is then free to reuse all of the data and the metadata which has been sent to them in part of their own processes. And that could be, for example, proving to accreditors that their traceability chain is valid, that it's not been broken at some point. So as a quick summary of what I've been talking about today, the digitalization of the SI meter is very definitely underway. We've seen the unique SI reference point, and I apologize for the typo here, it should be S capital I, the unique SI reference point at the top of the chain. We've seen a little bit of a quick look at the digitalization of the database of the frequencies which the NMIs are using for a lot of their meter realizations. I've presented some work which is starting at the moment on making the mise en pratique data available in an XML format, and then describe this XML schema, which you can go and look at from the repository, which was shown earlier. And I've talked a little bit about the benefits for the various stakeholders, which includes the end user, the NMI or DI, and also the BIPM and CIPM. Before I finish, I'd like to acknowledge all those who've contributed to this work, obviously those within the CCL structure for the instigation of this work, my colleague Andrew Lancaster at NPL for the detailed design of the schema, and Aurélie at the BIPM for the software development of the CCL and CCTF database. And if this all sounds a little bit like something from the future, let me give you a very concrete example of where it's happening right now. So this is a new mise en pratique NPL laser for realizing the meter. And this laser is computer controlled using a small computer on board. And this laser will be talking to the BIPM servers as soon as they make the data available. And this laser will then be downloading the digital traceability data direct from the BIPM server. And so with that, I will say thank you. And thank you for this opportunity to present the work today.
Well, thank you, Andrew. That was really fascinating. And I think not only the detailed work that you've shown, but that link from the digital world directly controlling of physical representation realization of the meter is a really nice visual that I hope everyone's able to take away from today. We don't have much time for questions, and I'm sorry, especially for Daniel, who's been posing all week long as Joachim. So that was the most pressing question that I saw in the discussions. Some of the other more technical questions have been deferred, and Stuart Chalk will be able to work with us offline to answer them. But I see in the questions there is a question I'd like to address, because it does sort of wrap things up and set the scene for why we all have to work together. And Daniel, posing as Joachim, asks about the authoritative ground truth source for the CODATA fundamental physical constants. And I think it's nice to remember that the CODATA fundamental constants group is responsible for the best adjusted values for many physical constants. But the subset of those constants, which we now use as the defining constants of the SI, they're not part of that adjustment anymore. They're fixed for all time, or until the next time we change something. They're fixed for all time, and they're just defining values that express how we work within the SI. So that subset of 8 constants that we use in the SI are in the purview of the CIPM and the definition of the SI, whereas the best adjusted values from the work of the CODATA task group that comes out, those will be in the repository of the CODATA presentation. Obviously, this is a very close collaboration, because not only does the CODATA data set have to show the same CIPM values for the fixed ones, but it also has to link back to it and make sure that everything is tied together. They do that already in a very careful way, because they use those fixed values as part of the adjustment process. So there's very unlikely to be anything going wrong there. But it does illustrate some of the complexities of interoperability and reusability as we move into the next phase. With that, Martin, unless you have any other final closing comments, I'd like to thank our more than 80 participants and all of the speakers and the organizers for making this work today. Technical glitches aside, I found this really fascinating. Martin, to you for a final word.
Thanks very much, and thanks to all the colleagues and to Andrew coming in to show what's really going on now and how close we are. As you finish this, the last slide was the most appropriate, that this is really actually in hardware now in a lab, providing what we're really after, which is a new service, a new capability, and that's what the digital transformation holds for us. So thank you very much for everybody. We will make the recording of this and the slides available online probably early next week. Thanks very much.